realistically, it's because the water could not possibly lift up the mercury because the weight of the mercury is more than the weight of the water, so the buoyant force on the water would be greater than the buoyant force on the mercury. And so the two couldn't mix. So we get a case. And by the way, this happens all over. This is a huge thing, okay? Especially when you get into meteorology and oceanography, okay? Fresh water does not mix with salt water, and we get these things called haloclines, where fresh water is flowing over the salt water. It's all water, but you can get a tunnel of water inside of water, right? And we actually have a lot of problems with that right now. We're very concerned about some of those haloclines and some deep ocean currents because, well, we need them to be the way that they are if we want things to grow the way that they do. And they look like they might shut down. Sorry. Okay, moving on. And then we pour oil on top of water, right? And we all know that oil is less dense than water. Or if you didn't know that, surprise, oil is less dense than water. And that comes out pretty, right? You know, down here you got a silvery substance. Here it's clear, and then here, you know, you get the kind of a yellow color, right? And they actually, you know, they layer up, right? You can actually see the layers between them, right? Now, but the fun part comes, right? And unfortunately, I'm kind of stealing the thunder of it. But I will show it to you. When you drop objects into it, right? Now, when I was a kid, we could do this. We can't do this now, right? But if you slowly, right, you don't like throw it in, because we don't want to cause the liquids to get all crazy. But if you slowly put a, you know, metal fastener, i.e. a nut, right, into the density column, what is it going to do?
Sink.
It'll sink. But actually what will happen is it'll come down and it'll sit right there. Actually, it'll stick a little bit below the surface. Because steel is less dense than mercury, even though mercury is a liquid. So it'll sit there and float on top. And then we drop in, you know, some kind of you know, heavier substance. Some kinds of plastics are just barely light enough to where they'll float. Okay, with PTFE and some other stuff. Right, so you drop that in, and what happens? They sink down, and that box of plastic sticks between them. And then lastly, you know, you might throw in some like leaves, you know, leaves, pieces of a leaf, or something really light, and then they'll float on the top. If you leave it there for a long time, it won't change. So what it demonstrates is that objects will sink, right? The easy way of saying it is they'll sink, you know, in a fluid that is less dense than them, because that's the sink or float game. But realistically, it's because that object is displacing, right? If the weight of the object is more than the weight of the water being displaced, then it will fall to the bottom because the buoyant force isn't high enough. Until it gets to a liquid where the weight of the water being displaced is equal to the object, and then an object will balance. So this is kind of an important concept because you might see this again shortly. Yeah. Questions? Cool. Moving on. Okay, y'all are gonna be real ready for the test and don't forget everything I just did. Let's see here. Okay, what is the condition that makes an object float? We've talked about it like 5 times, but this is super important because you got to know it. What? Yeah, but what is the condition? Yes, buoyancy is part of it, but you can have buoyancy and still sink.
Pressure.
Because buoyancy just means there's a buoyant force.
When the force of the object pushing down is the same as the force pushing back up on.
Okay, so this is super important. Please listen. Okay, engage. in order to not sink. Oh man, I erased it. Oh well, that's fine. Water, boat, solid boat of wood, so we don't have to worry about the whole mixture thing, right? If this piece of the boat, right, the water that got displaced, H2O, that got pushed out from when the boat got pushed on, if this weight is equal to the weight of the boat, that's an A, not a weird thing. And so this is going to be weight, and that's going to be weight. If the weight of this water is equal to the weight of the boat, then it will float. That is the condition that causes objects to float. Can you float in the middle of the water column? Absolutely. Okay, that's called neutral buoyancy. Right? But you must know this. Okay. All right, now let's see here what else. Talked about that yesterday. Oh, okay. So there's just something we did not cover at all. So this is important. Okay, important. So there's a concept in physics, and it is rarely used in the mechanical universe. We use it all the time in the electrical universe because we deal with fields and things like that. And this is important. Please listen. There's a concept of flux. Okay, flux. And just in case you're hard of hearing, it's flux. Okay, flux.
I don't get it.
Now, so what flux is, means if you have a enclosed surface, right, a loop of some sort, or it could be a square, it doesn't have to be a loop, it could be any shape whatsoever. That's a circle, by the way. Okay. It's not a good circle because I'm trying to show it in 3 dimensions. Right. And if I have something flowing through that enclosed space, right? And so that comes out to the other side of that area. So the water flows through this open space, maybe it's a pipe, whatever it is, and then it comes out the other side. The flux is the amount. It's the amount of stuff that's flowing through a closed area. Now, just to be overtly helpful, if I were to quadruple the size of this hoop, right? I still have the same flow going through the much larger hoopy thing. Actually, there. Keep the imagination going.
Oh wow, that's the line.
That's me.
Can I use the restroom?
And of course you may. If the pass is there, y'all can use the pass. You don't have to ask me. Okay, y'all are adultish, so I trust you. Yes.
Is the flux the discharge or the discharge rate? Or both?
Say again?
Is it the discharge or the discharge rate? Or is it both?
It's the discharge rate. So how much is flowing through it per unit time? Thank you for asking that question. So it's the volume of whatever that is per unit time. When I'm talking about fluids. When we're talking about electricity, then it's the strength of the field through that enclosed area. Magnetism, same thing. Electricity and magnetism, you do flux all the time. All right, now, so increased the size of that hoop by 4. Right? The flow is the same. So how much did the flux increase by? Say again? That would be a good guess, okay? And no, seriously, thank you. But what I want, let me give you a hint, okay? I'm gonna give her a chance to redeem herself first, okay? Think circle, think area. If you quadruple the area of a circle, right, then what factor has to change in the, right, so if you make the radius 4 times bigger, in the area equation, what happens to the total surface area of the circle? What's the equation? What's the equation? What's the equation for the area of a circle? Pi what? Pi r squared, exactly. So if I make the r 4 times bigger, right? Then what happens to the total area?
Increases by 4 pi, or 4.
Does the pi change? No, because it's just pi, right? So where's the 4? The 4 applies to the r. So let's look at it on the board, okay? Let's look at it on the board. I'm going to give somebody else a chance to answer it. I'm still going to show it to you on the board, okay? Anybody else want to take a stab at this? Okay, so nobody knows for sure. Okay, fine. And I'll just show it to you on the board, and then you all will know for sure. Okay, because this is important. You will use this skill. I cannot tell you the number of times you will use this kind of a skill with doubling and tripling and halving and all those other kinds of things, right? So if I have pi r squared equals some number, right? And I got to do the same thing to both sides, right? That's what algebra tells us. So if I put pi and then I put a 2 over here, what happened to the area? Did it get 4 times bigger? No, because we multiplied radius first before we squared it. So when you double something that is already being squared, then you quadruple the size of it. If you quadruple the size of something, so here I don't know why I put a 2 there. That's why y'all are confused. If I put a 4 here, then that's 4 times r, right? Because it got 4 times bigger. But the value of this, right? Now I have 4r, and 4 squared is 16. So by putting a 4 here, what I've done is I've increased the value of this side by 16. Okay? And so algebra says I have to do the same thing to both sides. So if I increase the value of this by 16, then I have to increase the value of the number by 16. It would be exactly as if I did this. If I put a 16 on that side, because I increased the value by 16, then in order for them to be equivalent, I have to value this by 16. Because they must still equal each other. So if I square a number or quadruple a number that is then squared, then the value of it doesn't just get like 4 times bigger or 2 times bigger. You have to take the square of that. Does that make sense? So we'll try it in a different way. We'll stay out of the 3-dimensional stuff, right? So what if? Oh, I don't know. What if I make this 2 times bigger? What if I make that twice as big? What have I done to the flux that would flow through it? If I had some kind of field, some kind of water flowing through this, you get the point. And I doubled the size of it, what would happen to our value? What would happen to the flux? You can just use your mind and complete the little drawing.
Quadruple?
You quadruple it, right? Because the square, yes, it's length times width, absolutely, right? But if I'm gonna make a square twice as big, then I gotta multiply that times 2. But that wouldn't make it twice as big, right? And then I'm gonna multiply this times 2. And so I would end up making it 4 times bigger. And I could also imagine that. So flux goes through this, look at that, through that.
Does the flux change depending on the container? Like if it's smaller, the flux will be smaller, and if it's bigger, the flux will be bigger?
Yes, if the volume flow rate is the same, then yes. Okay. If you're like Bernoulli's equation, where you have a different volume flowing through it because you've squeezed it down, then that's another story. Okay. Is everybody okay with this? So if let's just to check verbally, right? If I double the radius of a circle, what's going to happen to the flux through it? Yeah, it's going to get 4 times bigger because it's r squared. You're not squaring the r squared, or you're not multiplying r squared times 2. You're multiplying r times 2. And then you have to square that. Okay. All right. Important concept. You will see that again. I pinky swear. Square.
Oh my God.
So, what else? Gotta be super awesome. Yes. You don't even have to convert that one. That's nice. You want to do a Bernoulli's equation one? Why don't we do that? The Bernoulli's equation. Not Bernoulli's equation, sorry. Pascal's equation. Sorry. Pascal's equation. All right, now, so I have a piston, a small piston. It's attached to a larger piston. And so both of these, it's fully, there's no air in there, it's completely full to the top. So anything you do this side is going to do this side. Okay. And we're going to say that this piston over here is 4 times larger than that piston. Okay, 4 times larger. If I push down on this piston with 50 newtons of force, what is the force delivered to the box sitting on that piston? Huh? So what?
What's the 4?
The 4? That means this piston is 4 times larger than that. Okay, I'll say it again. So the question is, if I have 2 pistons that are contained, right? I push down on this piston with 50 newtons of force. The piston over here, the larger piston, is 4 times larger than this one. How much force is delivered to this box? How hard does this thing push up? 4 times larger. These are the kinds of words that you need to understand in questions. Sometimes the wording in a question and how you visualize it makes all the difference in the world. So when you're visualizing this, when I say 4 times larger, what are you thinking? Are you thinking surface area is 4 times larger? Or are you thinking radius is 4 times larger?
Surface area.
What?
Surface area.
It's actually radius, right? Because if you make a hoop twice as big, you're going to make it twice as big, right? You're not actually talking about surface area. Right? Now, most of the time, but not all the time, they'll say it has twice as much surface area. But if they say it's twice as big, then they're talking about radius. Okay? Then they're talking about radius. So now that I've, elucidated that fact, right? I love that word, elucidate. So now that I have shown you that fact, made it clear, how much do we have there? What's the force? What? It's more than that, I think. Because this one's, the radius of this is 4 times larger than that.
Is it 800?
Let's see here. So it's 16 times 50, right? 500, 300, 800. Yeah, 800. I just want to double check. It's early in the morning. I haven't had my coffee. I've had no coffee. Okay. Now, next question for you. If I push this one down, this is important. If I push this one down 10 centimeters, how far does that one go? It'd be the reverse. It'd be 10 divided by 4. If you get more force, you get less distance. Just remember that. Okay? More force, less distance.
More force, less distance.
Either one. I just memorized more force, less distance.
Okay.
They're opposite.